A lot of non-Newtonian fluids are present in our daily lives, such as toothpaste, jelly, cheese, or even saliva are examples of this. Initially, a non-Newtonian fluid doesn't follow Newton's law of viscosity, and these kinds of fluid are best studied through their rheological properties, which show the relationship between the applied stress on the substance and the strain rate under different flow conditions. This experiment consists of recording the variation of the average speed of displacement of a body completely immersed in a plastic measuring cylinder test tube with 500 milliliters of the fluid. Consequently, we developed a simple methodology to observe the non-Newtonian behavior of a fluid composed of water and cornstarch. Setting up the system. 2 universal supports perpendicular to the table with a prominent hook parallel to the table on each of the supports. A nylon thread was passed through these hooks with a steel spheric body attached to one end, with a plastic measuring cylinder test tube containing the non-Newtonian fluid from which the ball would emerge. The other end was attached to a wooden platform where weights were placed. Throughout 3 different concentrations of cornstarch and water, the tests carried out consisted of measuring the time it took for the ball to reach the surface according to the change in the load that pulled it, and was possible to observe that during the flow, the apparent viscosity is not constant. With that data and the known height of the liquid of 24 centimeters, we can measure the average speed, then watch the impact of the applied tension in that value. As we increase the tension, the deformation of the liquid increases, applying resistance in the movement of the immersed body. In all cases, a trendline equation of second order was calculated. To obtain the exact value of the tension applied on the liquid, we schematized and related the forces that influence the body immersed in the liquid as the following. We concluded that the forces that act in favor of the vertical displacement of the body immersed in the liquid are the buoyancy force and the weight force of the system. The force acting against the vertical motion of the body is the weight force of the ball. However, considering that it is a non-Newtonian dilated fluid, in addition to the forces mentioned above, the movement will also produce a resistant force due to the deformation of the liquid after being subject to shear stress. Finally, we have deformation resistance is equal to F minus S. We cannot measure the value of the resistance force that will act in a body as a response to the applied shear stress, but we can measure the velocity of the body and see how this force impacts the movement. So we can measure the shear stress applied and the speed of the body, considering that the speed of the body may decrease as we increase the F force. For all tests, we use the same parameters, only changing the fluid concentration and assuming the mass is not one of the main parameters of the test. Following the operation logics of rheometers, we created a system where it was possible to apply stress to the liquid in a controlled manner. So instead of having the shear stress as a result of the applied shear rate, we had the resulting velocity of a body immersed in that liquid, which is a response of the liquid deformation rate. Besides, we could see that behavior of all analyzed fluids deviates from the classic Newtonian behavior of viscosity. Furthermore, in some cases, we observed a slight decrease of the body's speed. That behavior allows us to conclude that this fluid must be a non-Newtonian kind of fluid, showing better its properties in concentrations between 120 and 130%.